Hello everyone, I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today, I'm going to start a series of lectures on engineered electric and magnetic materials. And under this head, today I'm going to just discuss about the introduction to dielectrics. So we'll be discussing mostly about dielectrics today and the terms and definitions that are involved with dielectrics. So when it comes to dielectrics, what are dielectrics? They are nothing but insulating materials. So when we say insulating materials are those which do not allow the heat or electricity to pass through them. And why they behave, these dielectrics are insulators? Because all the electrons are bound to their parent molecules and there are no free charges. So whenever we are talking about the structure of an atom, we have the nucleus at the center and electrons revolving round the nucleus in fixed orbits. Now, if the electrons in the outermost orbit are bound to the nucleus and they cannot be made free easily, then you call them as dielectrics. Means even with normal voltage or thermal energy, these electrons cannot be released. Because in some materials what we see is whenever an external supply is given, these electrons can be freed. The electrons come out, they become free and they start conducting. But in case of dielectrics, even when we are applying an external voltage or giving thermal energy, these electrons are not released. That is why we say they are bound and there are no free electrons. And the dielectrics are non-metallic materials. They are not metals. Metals, if you see, they are very good conductors. So dielectrics are non-metallic materials of high specific resistance. They have very high resistance and negative temperature coefficient of resistance. Means as the temperature increases, the resistance decreases. This is what we need to understand about dielectrics. Now, these materials which behave like dielectrics, they have an energy gap of 3 electron volt or more, and we call them as insulators. So what is an energy gap? We will try to understand the energy gap. Whenever we draw an energy band diagram, this is the conduction band, this is the valence band, this is the topmost level in the valence band, bottommost in the conduction band, and this is what we call it as energy gap. Energy gap is the difference between EC and EV. So, in case of insulators, the energy gap is 3 electron volt or more. Means if the gap is more, we need to supply more energy to move the electrons from the valence band to the conduction band. Only when we have electrons in the conduction band, they start conducting. So, in these materials, it is not possible to excite the electrons. Why it is not possible? Because the energy gap is high. The energy gap is greater than or equal to 3 electron volt. Only when you supply an energy much greater than this, we can move the electrons from valence band to conduction band. So, materials such as glass, ceramics, polymers and paper, all these are non-conducting materials. They do not conduct. So, they can be used as insulators. And when the main function of the non-conducting material is to provide electrical insulation. So, whenever we are using these dielectric materials for electrical insulation, to insulate or to not allow the current to flow through, then we are calling them as insulators. Now, these dielectrics allow the movement of some electrons at abnormally high temperatures. I said the energy gap is more than or equal to, it should be more than 3 electron volt. So when you are supplying temperatures or heating it to very high temperature, so that this energy gap can be overcome, only then a small current will flow due to the movement of electrons. So dielectric materials are electrically non-conducting. So I can say they are non-conducting and they are insulators. They can be used as insulators. And whenever we are talking about a non-conducting material, its function is to store the electrical charges. They are used to store electrical charges. That is why these non-conducting materials we are calling as dielectrics. The name dielectric comes from this function because it is used to store electrical charges. And in practice, if you see, dielectrics conduct electric current to a very negligible extent and their resistivity varies in the range 10 power 10 to 10 power 20 ohm meter. We are talking in terms of resistivity. So that is ranging from 10 power 10 to 10 power 20. Now, they are possessing high resistivity values in the range. Some of them have from 10 power 6 to 10 power 16 also. So, under high voltage bias, they allow very little current. So, the bias or the temperature that we have to apply should be very high. And they can also withstand very high voltages. When we are applying such high voltage, that should not break down. So, they can withstand very high voltages. And the conduction here is mostly associated with ionic motion. That is through defects or hopping of the charges. Hopping of charges from one side to the other side. That looks like a movement of charge or ionic motion. So, it is mostly due to the ionic motion. Now, here in dielectrics, we have seen that there are no free charges. So, the electrical properties of a dielectric are associated with the property of possessing dipoles or electric dipoles. So, when there are no free charges, how do we explain the electrical properties of the dielectric? So, this can be explained based on electric dipoles. In the next few slides, we are going to discuss about what are dipoles and how they behave. So, dielectrics are materials which have an electric dipole moment permanently or temporarily. Some of the dielectrics have a temporary dipole moment, means they will form dipoles when subjected to electric field, or sometimes they become permanent electric dipoles. And they are mainly used to store electrical energy. So, we have already seen the main function is to store electric charges. So, these dielectrics are used to store electrical energy and also they are used as electrical insulators. Now, when it comes to dielectrics, all dielectrics are electrical insulators. So, whenever I am talking about a dielectric, it is insulating. It can be used for electrical storage. But will all insulators be dielectric? No. So, all electrical insulators, they need not be dielectric. We take the example of vacuum. Vacuum is a perfect insulator, but it is not a dielectric. You cannot store charges in it. So, all dielectrics can be insulators, but all insulators cannot act as dielectrics. So, the study of dielectrics is essentially the study of insulators. Now, coming to the definitions, first we are going to see what an electric dipole is. Electric dipole. So, two equal and opposite charges separated by a distance r constitute a dipole. So, very simple definition. Two equal, means they should be equal in magnitude. Two equal charges means equal in magnitude and opposite. The charge should be opposite and they should be separated by a distance r, and that forms a dipole. You can see in the figure here, we have taken two charges, plus q and minus q. When I am writing q and q, means here the magnitude is the same. But if you see the charges, this is plus q and this is minus q. So they are opposite charges. So these two charges, plus q and minus q, they are separated by a distance r. I am talking about the separation from the center of the charge to the center, which is denoted by r. So such an arrangement, we are calling it as a dipole. Di means two. Two charges which are equal in magnitude and opposite in charge, they are separated by a distance and they constitute a dipole. Now coming to the electric dipole moment. We simply say it is dipole moment or electric dipole moment. So what is electric dipole moment? It is the product of the charge and the distance between the two charges. We said two charges separated by a distance r forms a dipole. Now how do we calculate the dipole moment of the dipole that is formed? So the dipole moment is given by mu. Mu denotes the dipole moment. Is the product of q, the charge, and the distance between the two charges. Here we are taking only the magnitude of one charge. I said they are same in magnitude. We are not considering the direction here. So mu is equal to, mu is what? The dipole moment or electric dipole moment. So this is plus q. This is minus q. They are separated by a distance r. They are equal in magnitude and opposite in charge, and they constitute a dipole. And the dipole moment is given by QR, Q into R. And the units for this dipole moment, Q is measured in coulomb in SI system and R is measured in meter. So we can write the unit as coulomb meter. Or we can also use dBi. In some books they use the unit dBi. What is 1 dBi equal to? 3.33 into 10 power minus 30 coulomb meters. So the smaller unit for coulomb meter or the dipole moment is dBi. Now coming to the direction of the electric dipole moment, it always has a direction is from positive charge to negative charge. The direction of the dipole moment is from positive to negative. Now let us see two examples. We have taken the molecule CO2, carbon dioxide molecule. So here C is positive and O is negative. So I have taken C here, the positive charge, and O here, and here two oxygens we have, two O's. They are separated by a distance. Now, what is the direction of the dipole moment from positive to negative? So this is positive, C. So this dipole moment here will be from C to O. And again we have an O here. The direction is again from C to O. Now if you see the molecule as a whole, what will be the net dipole moment? We call it as net dipole moment or overall dipole moment. They will cancel each other and the net dipole moment will be equal to 0. So in case of molecules like this which are symmetrically arranged, and since the direction is always from positive to negative, here we have two oxygen molecules and these two are direction and equally spaced. So the net dipole is equal to 0. Now let us take another example of H2O, water. Two hydrogen molecules and one oxygen. So hydrogen is positive and oxygen negative. So how we are drawing the diagram? This is one hydrogen and this is another hydrogen and this is oxygen. H2O. Now, how is the dipole moment? Always from positive to negative. So this is the dipole moment between H and O, and this is the dipole moment from H and O. Now, in this case, the dipole moments will not cancel. So, if you take this molecule of water, there will be a net dipole moment. So, I say the net dipole moment is not equal to 0. There will be a net dipole moment, means there will be some overall dipole moment. Now coming to the next definition, dielectric constant. What is a dielectric constant? This dielectric constant, which is denoted by epsilon r, we call this as epsilon. Epsilon r or relative permittivity. We also call it as relative permittivity of the medium. So how do we define this dielectric constant? It is the ratio between permittivity of the medium and the permittivity of free space. So how we are writing? Epsilon r is representing the relative permittivity or dielectric constant. It is the ratio. Ratio of what? Epsilon. Epsilon is what? Absolute permittivity of the medium, and epsilon naught. Epsilon naught is the permittivity of free space. Whenever we are talking about epsilon naught, it is the permittivity of free space and its value is constant. 8.854 into 10 power minus 12 farad per meter. This is the value of epsilon naught. So to calculate epsilon naught, what we do? We take the ratio of epsilon and epsilon naught. So we have the formula as epsilon r is equal to epsilon upon epsilon naught. So the unit for epsilon is farad per meter, and because we are taking the ratio, the dielectric constant has no units because it is the ratio of two similar quantities. So it has no units. Now coming to polarizability. What is polarizability? The average dipole moment mu, we have discussed about dipole moment. The product of charge and the distance gives us the dipole moment. This is directly proportional to the electric field. What do you mean by directly proportional? So as the electric field increases, the dipole moment also increases. So mu is proportional to E. E here is the electric field and mu is the dipole moment. So dipole moment is proportional to electric field. Now I can remove the proportionality sign and put a constant alpha. So I can write it as mu is equal to alpha E. What is alpha here? Alpha is the polarizability. We are trying to define the polarizability. So polarizability is equal to mu upon E, that is farads per meter. So we can define this polarizability as the induced dipole moment per unit electric field. So if you have to write the definition for polarizability, it is the induced dipole moment per unit electric field, and the formula is alpha is equal to mu upon E. This is the formula. And what are the units? Farad per meter square are the units for polarizability. Now coming to polarization vector. This polarization vector is denoted by P. And we define polarization vector as the average dipole moment per unit volume. So the average dipole moment, if you take per unit volume of the dielectric, then we get the polarization vector. And if there are n molecules that are present in unit volume, when we are considering a volume and there are capital N number of molecules, then the polarization vector P will be equal to n into mu. upon volume. So we have to take the total number of molecules into consideration to calculate the polarization vector. Or there is another notation to write P or to represent this polarization vector P. So P is equal to sigma I to N Qi into Xi. So when I am talking about Qi into Xi, Q is the charge and X is the distance. So this gives Q into X gives us the dipole moment, and we have to take the sum of the dipole moments of all the molecules, of all the N molecules. So I may take from I is equal to 1 to N divided by volume, that gives us P. So to calculate the total dipole moment per unit volume, which gives us the polarization vector. And the unit is Coulomb per meter square. The SI unit for polarization vector is Coulomb per meter square, because we have here for the charge we have Coulomb and the distance is in meter. The volume is always in meter square. Sorry, volume is in meter cube. So we get the unit as Coulomb per meter square. Now the next one is electric polarization. What is polarization? And if it is due to the electric field, we call it as electric polarization. So when we are keeping a dielectric substance in an electric field, we have taken a dielectric substance and we placed it in an electric field, then the positive and the negative charges are displaced in opposite directions. So here there is an electric field. This is the positive and this is the negative. An electric field, and in this electric field we are placing a dielectric substance. So this is the dielectric substance we have placed in the electric field. Then what happens? The positive and negative charges in the dielectric are displaced in the opposite direction, means towards the positive plate we get the negative and towards the negative plate we get the positive. So this displacement of charges produces local dipoles. So what are dipoles? Dipoles are nothing but equal and opposite charges separated by distance. So I can say this forms one dipole, this forms one dipole, and so on. So this displacement of charges produces local dipoles. Now the process of producing electric dipoles inside a dielectric by the application of electric field. So what we did, we have taken a dielectric substance and we have applied an electric field. And when we did that, what happened? There are electric dipoles that are formed. This process we are calling it as polarization. So it is the process of producing electric dipoles by the application of an electric field in a dielectric. Now comes the electric flux density or electric displacement, which is denoted by capital D. The flux density or electric displacement both mean the same and it is denoted by capital D. So how do we define this flux density? The number of electric lines of force received per unit area. Number of lines of force, electric lines of force received per unit area is called as electric flux density. And this electric flux density is directly proportional to E. Means if the electric flux increases, the flux density also increases. So that is the meaning, directly proportional. So now I can remove the proportionality sign and put a constant. D is equal to epsilon E. What is epsilon here? It is the permittivity of the medium. Permittivity of whatever medium we have taken, its permittivity. And we also have seen that dielectric constant epsilon R is defined as the ratio of permittivity of the medium to the permittivity in free space or vacuum. So I can write simply epsilon is equal to epsilon naught into epsilon R. That is what we have taken. And we are going to substitute this value here in this expression. So what do we get? D is equal to epsilon naught epsilon r into E. So this is the expression for the electric flux density or the electric displacement. Now, this also is defined as the charge per unit area, and it has the same units as dielectric polarization. Now, when we are talking about the flux density at a point in free space, if I have to write the flux density in free space, then I can write it as D naught is equal to epsilon naught E. D naught is equal to epsilon naught E gives the flux density in free space. Now, in any medium, if you take whose permittivity is epsilon, the flux density is denoted by D is equal to epsilon E. So, we can, knowing the electric field and the permittivity of the medium, we can easily write the flux density. Now, as the polarization means the additional flux density that is arising from the presence of a material as compared to the free space. Means what we do here, we consider P as the polarization of the dielectric material due to the applied field. So we have already seen in polarization, whenever we are keeping a dielectric material in an electric field, there exists a process of polarization. They get separated in the opposite direction, and then the flux density should be equal to the flux density in vacuum plus the polarization. So how we are going to write the flux density D is the density in vacuum, flux density in vacuum, that is epsilon naught E plus P. P is the polarization due to the electric field. So what is the final formula we are getting? For the flux density, it is the flux density in vacuum plus the polarization. So we have written epsilon naught E plus P. Now when we have D is equal to epsilon naught E plus P, what is D here in a medium? In any medium, if you take, we have seen that D is equal to epsilon E. So let us substitute it here, epsilon E. For D, I am writing epsilon E, and that is epsilon naught E plus P. Now if I have to find P, I'll just transpose, take it on to the other side. So P will be equal to epsilon naught E minus epsilon naught E. So what we are doing here basically is D is equal to epsilon naught E plus P. So for D, we are going to substitute from this equation 1 in equation 2. So epsilon E is equal to epsilon naught E plus P. So if I have to find P, I'll take epsilon naught E onto the other side. So P will be equal to epsilon E minus epsilon naught E. Now we have the basic formula. What is epsilon? It is epsilon naught into epsilon R. Epsilon is equal to epsilon naught into epsilon R E minus epsilon naught E. So I can also write it as P is equal to epsilon naught E into epsilon R minus 1. So this is the formula we get for polarization in terms of permittivity and electric field. Now we are going to define electric susceptibility. What is electric susceptibility? It is defined as the ratio of the polarization vector to the intensity of the electric field. So we can define susceptibility, which is denoted by chi. This is a Greek alphabet, chi, we say. So chi is defined as the ratio of the polarization vector P to the intensity of the electric field. So chi is equal to P upon epsilon naught E. Now we have already got the formula for P. What is P equal to? We got in the previous this thing. It is epsilon R minus 1 into epsilon naught E. This is what we have got the expression for polarization. So I am going to substitute this here in this equation 1. What we get, epsilon r minus 1 into epsilon naught E by epsilon naught. So this epsilon naught E will get cancelled. So what we are left with is chi is equal to epsilon r minus 1. So the susceptibility is given by epsilon r minus 1. What is epsilon r here? It is a dielectric constant or the relative permittivity. So chi depends upon the dielectric constant of the material. If you talk in terms of its significance, the susceptibility is the tendency of that medium to allow the lines of force to pass through it. So it will definitely depend upon the permittivity. Then comes the dielectric strength. What is dielectric strength? The minimum voltage that is required to produce an electric breakdown. The dielectric breakdown means it is the failure of an insulating material to prevent the flow of current. Whenever we are talking about an insulator, it prevents the flow of current. Now, when an insulator breaks down occurs, dielectric breakdown occurs, then it cannot stop the flow of electrons. So, it is the failure of an insulating material to prevent or to stop the flow of current under an electric stress. This is also important. So, dielectric strength decreases with increase in temperature, humidity and age. So, as the temperature increases, dielectric strength decreases. And as the humidity increases and also with the age of material, means as the material becomes old, then what happens? The dielectric strength decreases. Now coming to polar molecules. In nature, we have some molecules which are polar in nature. And these polar molecules are unsymmetrical. They are not symmetrical in nature. That's why we say they are unsymmetrical. Because of their unsymmetrical nature, they have a permanent electric dipole moment. So we have seen in the beginning. So whenever we talk about dielectrics, they may possess temporary dipole moment or permanent dipole moment. So here when we are taking about polar molecules, for example, we have taken H2O, HCl, CO, N2, NH3. All these molecules, because of their unsymmetrical nature, they have permanent electric dipole moment. So we have already seen the example of H2O. H is positive, O is negative. So the dipole moment is always acting from positive to negative. So in this case, they don't cancel each other. So there is always a net dipole moment. So for a H2O molecule, the dipole moment is 1.84 D. And the same with NH3, HCl and CH3Cl. All these molecules will have a net dipole moment. Their mu is not equal to 0. Such molecules we call them as polar molecules. Now we have polar dielectrics. What are polar dielectrics? So simply speaking, polar dielectrics are those materials which are made up of polar molecules. Means the center of gravity of the negative charge distribution may not coincide with the center of positive charge. If they are not coinciding, means there is an effective separation between the centers of negative and positive charge, then they will have a net dipole moment. And then we call them as polar dielectrics. So in a polar dielectric, we need to have dipoles. So what is a dipole here when we are talking about the dielectric as a whole, which has a large number of molecules? The effective positive and the negative charges, they are separated by a distance. Then they will have polar dipole moment and they are called as polar dielectrics. So now how are the electric lines of force in a polar dielectric? So when we are talking about a polar dielectric, if this is the external field and this is the dielectric we have placed, so what will happen if positive and negative electric field? On placing the dielectric, this is the dielectric we have placed in a electric field. So what we have seen, polarization will occur. So the negative and positive charges will get displaced in the opposite direction. Means towards the positive plate, we are having the negative charges, and towards the negative plate, we are having the positive charges. Now the lines of force, electric lines of force are like this. This is the direction of the lines of force in a polar direction. Now coming to non-polar molecule. Non-polar means the positive charge of the nucleus may be concentrated at a single point, which we call it as the center of gravity of the positive charge. And the negative charge is also supposed to be concentrated at a single point, and we call it as center of gravity of the negative charge. And when these two centers, means the center of gravity of the positive charge and the center of gravity of the negative charge, if they are coinciding with each other. So when they coincide with each other, then we call it as non-polar. So in polar, there should be a separation between the two, positive and negative, effective positive and negative charge. But here, if the positive charge and the negative charge, they are coinciding with each other, means the distance between them is equal to 0. Then what happens? These non-polar molecules, they have symmetrical structure and zero electric dipole moment. These type of non-polar molecules, they have zero dipole moment. Examples we have seen for CO2, we have seen O2, N2, all these are non-polar molecules. Now what are non-polar dielectrics? So if the center of gravity of the negative charge and the center of gravity of the positive charge coincide, that means these two equal and opposite charges are not separated. They are coinciding means what? They are not separated. So what is the formula for dipole moment? We have mu is equal to Q into R, and this R is equal to 0. So we are talking about the dipole moment of a non-polar molecule. So when the dipole moment is 0, when R is equal to 0. Because R is equal to 0, mu is equal to 0. Mu is equal to Q into R. So Q into 0 is equal to 0. And the materials or the dielectrics are called as non-polar molecules or non-polar dielectrics because their dipole moment is 0. Now what happens when we are placing a non-polar dielectric in an electric field? So when we are keeping a non-polar dielectric, means it is not polarized. Then what happens? So we have taken this non-polar molecule of a dielectric. This is the dielectric. When we have taken the dielectric and it is non-polar. Non-polar means what? The positive and the negative charges are coinciding with each other. So this is how they are coinciding with each other. This is when no electric field is applied. Now, what happens? Because they are coinciding with each other, R is equal to 0. So, their dipole moment is equal to 0. But when we are subjecting it to an electric field, means we have put some electric field here, positive plate and negative plate for this. Then what happens? The positive and the negative charges are reoriented. That is, the center of gravity of the positive charges are pulled towards the negative plate and vice versa. So, if this is the positive plate, all the negative charges are pulled towards the positive plate and all the positive charges are pulled towards the negative plate. So, when this happens, when we are placing this dielectric in an electric field, even though it is non-polar, but when subjected to an electric field, these charges are getting displaced. So the net effect of the applied field is to separate the positive charges from the negative charges. So there is polarization. So dielectrics which are polarized only when they are placed in an electric field are called as non-polar dielectrics. They are non-polar, but they are polarized when they are placed in an electric field. So here we can see the complete picture. So when there is no electric field that is applied, E is equal to 0, the positive and negative charges are coinciding with each other and the net dipole moment is equal to 0. But when we are applying an electric field, the positive and negative charges get displaced and here mu is not equal to 0. So in case of 0, it is like this coinciding with each other. Because of the electric field, they are getting displaced and because of which there is a net dipole moment. So what we are going to conclude now is, whenever we take a dielectric and place it in an electric field, induced surface charges appear and they will tend to weaken the original field within the dielectric. Why? Because this E prime, which is produced due to polarization, will always oppose the original field. So if the original field that is applied is E naught and the field that is developed due to polarization of charges in the electric field, they will oppose each other. So the net will be always less. So it will tend to weaken the original field. Now when we are placing a polar dielectric in an electric field, polar dielectric means which is already polarized, where the charges are separated. Means they have already permanent dipole moments. But these dipole moments, if you are taking these molecules all together, they have random orientations. Random means in any direction they want. If I am considering this dipole, negative, positive. But this is negative, this is positive. Like that. The positive and negative charges are separated in each dipole, but all the dipoles put together, because they are in random directions, they may cancel the dipole moments. That is in case of no electric field, when there is no electric field. But when we are applying an electric field, in the presence of an electric field, what happens? Partial alignment of dipole takes place. Partial alignment means all these negative will start aligning towards the positive plate and all the positives will start aligning towards the negative plate. So this is without the field, they have random orientation, and in the presence of an electric field, they are getting aligned. So polar dielectrics already possess some dipole moment inside because of the presence of permanent dielectric dipoles, but they are randomly oriented when no field is applied. Now, their dipole moment and polarization increases when they are aligned along the field. Means it gets some extra polarization. So now the polarization P will be equal to what? The polarization that already existing due to the permanent dipoles and the polarization that is induced because of placing it in an electric field. So how we can write the formula is, the total polarization P will be equal to the polarization due to the permanent dipoles plus the polarization due to induced dipoles. So P is equal to PP plus PI. So this is the formula for total polarization when we are placing a polarized molecule or a polar molecule in an electric field. So for more information regarding this topic, you can refer to books Introduction to Electrodynamics by Griffiths, David J. Griffiths. You can refer to this book. And also you can refer to Concepts of Physics by H.C. Verma. Concepts of Physics by H.C. Verma. I have given the reference also in the slides. So you can refer to these books for more information. Thank you and see you again.
Like, share and subscribe. Hit the bell icon for more updates.